Hello all. So today we're going to solve the Sudoku problem. So the question is to write a method that solves the Sudoku puzzle for us. So as you know, Sudoku is the 9 by 9 grid filled with digits from 1 to 9, and it has three conditions. So we should not have any repetitive number at each row, at each column, and at each 3 by 3 blocks. So one trivial solution that comes to mind is to write a bunch of nested loops and try all possible combinations from 1 to 9 and see if it works or not. The problem is that this is a very time-consuming and it's not very efficient approach. So how can we solve this problem a little bit more efficient? So there are ways to optimize our brute force solution. So one is constraint programming, and constraint programming is basically when we choose a number and place it in a cell, we immediately can exclude it from our search space so that as we proceed, we don't need to consider those numbers that we use already. The other one is backtracking. And with backtracking, I mean, let's say we manage to fill up some empty cells in Sudoku, and after some point we cannot go any further. Basically, we cannot choose any number from 1 to 9 to fill up a cell. So that means that in our previous attempts, so we did something wrong. So we filled up a cell by mistake. So we have to go back one step, change our previous cell that or previous number that we use for previous cell, and see if we can proceed. And if we cannot, then we have to go 2 steps back and fix that mistake, and then start basically trying the numbers after that. So this is the backtracking. Now let's actually go through this approach by example. So this is a grid, a Sudoku puzzle filled up with some numbers, and now we have to fill up the empty cells. Let's start from the first row and first column. Let's see if we can actually fill up the first row. So the first column is already filled. Let's go to the next one. Second one already filled. Next one is empty. Okay, so let's see if we can actually fill it up with 1. There's no 1 in the first row. There's no 1 in this column, and there's no 1 in the block here, right? So looks like we can use 1 in this cell. Let's go to the next column. We cannot use 1 because 1 already in this row and also in this column. How about 2? There's no 2 in this row, there's no 2 in this column, and there's no row in this block. So sure, let's go with 2 here. Next one is filled. We cannot use 1, 2, 3. How about 4? Yes, we can use 4. Next one. 1, 2, 3, 4, 5, 6. We cannot use 6 here because there is 6 in this 3 by 3 block. 7 we cannot use because 7 is already in this row. But we can use 8. Let's go to this one. We cannot use 1, 2, 3, 4, 5, 6, 7, 8, but we can use 9. Oops. And the last one, you can see that here, the only choice that we have for this row is 6, but we cannot use 6 because 6 already is here. So we don't have any choice here. So that means we're stuck. So what should we do? We have to go back one step and try to fix that. So let's go back. So here, can we actually use, we don't have any other choice here, right? Because we already checked 9, and 1, 2, 3, 4, 5, 6, 7, 8, and 9 also doesn't work. So let's go back one step further. So we tried 8 here. How about 9? and 8 doesn't work. So how about 9? 9, let's try 9 here. Go next one. So 1, 2, 3, 4, 5, 6, 7, 8. Sure, let's go with 8. Again, here we stuck. So go back. 8 doesn't work. 9 doesn't work. So 4 here doesn't work. 5 doesn't work because 5 is here. Sure, 6, we can do 6 here. Let's go to the next one. 1, 2, 3, 4. Can we do 4 here? Sure, we can use 4. Next one. 1, 2, 3, 4, 5, 6, 7, 8. We cannot because 8 is here. But we can do 9. And the only possibility here, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we can use 8 here. Perfect. So we've managed to finish the first row. Now let's go to the second row and basically do the same thing. So we keep doing this until we reach to the last row and last column. And when we reach at that point means that we solve the problem. Right, so let's talk about the complexity here. So when we use the complete brute force without any optimization, okay, so with no optimization. So what would be the complexity, the time complexity? So the time complexity would be we had to try 9 digits for basically all cells, right? So in that case, the complexity would be 9 to the power of 81. It's huge. How about our solution? So let's consider just the first row. So in the first row, when we choose a number here, we have, when there's basically empty row, for the first column or the first element, we have 9 choice, right? But as soon as we choose that number for the first element in that row, we should not use it, basically because we are using constraint programming, we exclude it from our search space. So for the next column, we have only 8 options. And for the next one, we have 7. So as you can see, for basically the first row, we have 9 factorial possibility. And how many rows do we have? 9, right? So the time complexity for our solution would be 9 factorial to 9. And if we compare these two numbers, you'll see that our optimized solution is 10 to the power of 27 times faster than the brute force without any optimization. So how about the space complexity? Well, the grid is 9 by 9, and in the worst case, all of them are empty. So the worst case space complexity is O of 81, which is a constant. Cool. Now let's see how should we code this up. So this is the Sudoku, like one example. It's being pre-filled by some digits, and there's some empty space indicated by a dot, right? So we have to fill up these dots basically. So let's define a solver class. And I mentioned that we don't need to okay. Right, so we'll start, as I explained, we start from the row 0 and column 0, okay? So, and then we go like recursively and see if we can finish the puzzle. Cool. So our basically solver will check if it's solvable or not. So if it's solvable, it returns the board. If not, it returns none. So our recursive solver gets the board and the row and the column. Okay. So what should we do like here? Right after we receive the board and row and column. So like I mentioned that what's basically the success criteria or the finish criteria. So if we are in the last row and last column, then it means that we actually solve, like fill up the last element, means that we solve the problem. Okay, so we say if row is equal to 9, means we're already good. Okay, so because it's 0 index, right? From index 0 to 8, and then if row is 9, it means that we already finished the puzzle. So if column is 9, means we finished the row and we have to go to the next row. So return self-recursive row plus 1, and we start from the first column. Also, if so if our board at row and column, okay, is not empty, means that it's already pre-filled, so we don't need to fill it up again, so we just go to the next column. Return row and what? Column plus 1. If none of these is satisfied, means that, okay, so we reached to an empty cell. Now let's try different numbers and see if it's working or not. So for the number in range 1 to 9, okay, let's convert it to character, because this is how our board has been made. So if we have to check if this number is valid. If valid, this row and column, and like this, then we just say, okay, board, row, column. Okay, so let's pause it here. How do we check whether a number is valid for this board, for this puzzle, at specific row and column? I mentioned that we have to basically, let's assume this. Let's consider, let me change the color. For example, let's see. For this cell, how do we know that if like digit, for example, 2 is, or digit 3 is valid or not? So we have to check the whole row, we have to check the whole column, and we have to check all elements in the block, right? So if for every single cell I check the whole column, row, and block, it's not going to be very efficient, right? So we have to do a more smarter way to check whether an element exists in specific column, row, or block. So a good data structure for that is a hash map. A hash map from particular row to the elements that row already contains. Same for the column and same for the block, right? So let's define our hash maps here. Rows and blocks. Now, let's actually fill up the rows and columns and blocks right at the beginning with the elements that already exist in the Sudoku puzzle. 9. If it's not empty, then so now, how do we know, for example, this INJ belongs to what block? Right, like here, this, what's the INJ here? So this is 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4, 5, 6, 7. Okay, so we know that our blocks are 3 by 3, right? So since we know that, it's easy. So we just need to do the integer division, like 4 divided by 3 is 1, 7 divided by 3, is 2. So it means that this element belongs to block 1 and 2. This is block 1. Sorry, this is block 0. This is block 1, okay. And now block 2. This is 0, 1, and 2. So this block is actually the block 1 and 2, okay. 1 and 2. So we can easily find out each element. So basically all the elements here belongs to block 1 and 2. Let's try this one, for example. This element is what? 0, 1, 2, 3. Again, 0, 1, 2, 3, and 0, 1, 2, 3, 4, 5, 6. Divided by 3 is 1, divided by 3 is 2. See? Now let's try this one, for example. 0, 1, and 0, 1. This divided by 3 is 0, and 1 divided by 3 is 0. So it's block 0 and 0. Correct. So basically, let's check the key here. The key would be I divided by 3 and j divided by 3. We say that, okay, now self blocks key at this element. Perfect. Now, for the valid, now it's easy basically. Valid, self, and character, right? So if ch in self, oops, sorry, for valid takes actually row and column and current candidate in rows row, or ch in columns col, or ch in blocks of row divided by 3 and col divided by 3, then return false. It means that this character already exists in either the current row, the current column, or the current block. So we shouldn't consider that, right? Otherwise, just return true. It means that this character is valid. All right, so if it's valid, we just add this to our, we replace the empty cell with this character, and we have to update our hash map. So we say that self rows of row, add this, calls, call, add this, and the key. What would be the key? So let's actually calculate the key here. Row now what should we do? Here we say that, okay, now that we actually replace that empty cell, let's check the rest of the Sudoku puzzle. So we say if self-recursive, the current row, but the next, let's move to the next column. If that actually is true, and if we keep doing that, we keep going deep and deep until we reach to the end of the puzzle, it returns true. If it's true, then basically we are good. Just return true. If it's not, means that we have to correct our solution, our previous steps. So it actually comes back here. So we have to say, okay, self board row and column, make it empty again, and remove the selected character from our hash maps. So self rows of row, remove ch. Okay, so basically this is the logic. Replace board row and column with character. Go to the next cell and check. If it's not successful, means that, okay, so here we did the wrong choice. So, revert the changes and try something else. Basically it goes up here and try different number, and if it's valid, it tries it again. Okay, so if we actually try all possible numbers at some point and we cannot find any good solution, we just return false. Okay, looks like it's we're done. So let's test it out. So we create our solver object, input, and then we say, you know what, solved puzzle, solver dot solve. I actually goes back here and do the recursion, and if it's true, then it returns the board, and we can basically see if it's working. Let's run it. Oh, there's a problem. So no recursion solver, where is it? Recursive solver. Oh, sorry. Any other issue? Cool. So yeah, looks like it's working. Now let's try this row. There's no repetition. And how about this block? There's no repetition. So yeah, it's working. And we also talk about the time complexity. Okay, that's it. Hope you enjoy this puzzle. So don't forget to subscribe and like. I'll see you next time.